Okay, well, the last kind of friction problem that we have to do is thrust bearings. So we're on bearings. We're done with this one. So now we're going on to the last friction topic. And we can think of this in general. Let's think about hollow tubes. So we'll do everything in terms of an inner and an outer radius, and then that works perfectly well for solid tubes too. You just have an inner radius of 0. And there's a force that's applied that way. We'll call that force P. And then there's, we're talking about a rotation like that. So it could be, well, there's always going to be some kind of couple. And so the frictional contact between the ground and the bottom edge of that tube also creates a moment. And if you're in equilibrium, that moment counteracts the external moment applied above. And so we are going to figure out how to calculate so what's the moment applied to the tube by friction? Well, the view that we're going to take for this is we're going to think of the cross-sectional area, that surface area that's in contact with the ground. So think of the area of the tube in contact with the ground. And we have an outer radius, R sub O, and an inner radius, R sub I. And we're going to do this derivation all in terms of this infinitesimal ring. Okay, so this ring has an infinitesimal thickness. We'll call that thickness dr. It's out at a distance of r from the center. So this is, so these two are capital R's because they're constants for the whole problem. But this r, can change, and then if you change that r to something between these two, you're just talking about a different infinitesimal ring. Okay. And so we're going to need to know the area of that ring. So the area is what we're going to call dA. It's an infinitesimal area because that thickness is infinitesimal. And we're going to calculate the area of that ring by imagining this is a trick that we use a lot with infinitesimal rings. Imagine detaching it here and straightening it out, and you get a long, skinny rectangle. What's the length of that rectangle? 2 pi r. Yep, it's the perimeter. And the thickness is dr, so that's the infinitesimal area dA. Okay, so we're going to do all these calculations in terms of these infinitesimal areas. There are 5 steps to doing this calculation. And you're going to need to be able to do this. The first one is, since we're going to be doing everything in terms of areas, in terms of these infinitesimal areas dA, we need to figure out the force per area. Okay. Then once we have the force per area, we're going to calculate the force on that infinitesimal ring. This is the normal force per area. So those are going to be related to that force P that's pushing these two things together. Once we have the normal force on that ring, we can calculate the friction force applied by that ring, or to that ring. Once we have that friction force, we can figure out the moment that that friction force applies. And then finally, we're just going to integrate. So the total moment is just equal to the integral from R inner to R outer of all those little infinitesimal moments produced by each ring. Okay, so let's go through this derivation. So that's kind of, so the normal force on the ring, I'm going to call this dN, and we're just going to go through this order. I think the best way to do it is just get in the habit of just doing it the same way every time and sort of ingrain it. But the normal force on the ring is d normal. The friction force applied to the ring, then the friction force is just the coefficient times the normal force. So that's going to be mu times that infinitesimal normal. The moment applied to the ring is going to be the moment arm times the friction force. So that's going to be R times mu d normal. And then integrate. Okay, so step 1 in this case. So the first thing we have to do is calculate the force per area. So that's just going to be the total force P. That's, if you look back at this picture, that's the force P that's pushing the surface and the tube together. And so we have the total force P divided by the total area. And the total area is pi r squared outer minus pi r squared inner, or pi times the quantity r outer squared minus r inner squared. So for any area region that we want, we can figure out the total force on that region by multiplying this times the area. So the second one is the total infinitesimal normal force on the infinitesimal ring. And this total infinitesimal normal force is going to be dN. I called it that because that's what it calls in the textbook, but it's just the force pushing those together. You'd call it whatever, but it's not. The thing I don't like about that is that force per area is actually a pressure, so it'd be sort of nice to use the P there, but I just use the same thing the textbook did. Okay, so the total infinitesimal normal force, dN, is just equal to the force per area times the area of that infinitesimal ring. So that's P over pi times the quantity r outer squared minus r inner squared times dA. And that's equal to P over pi times the quantity r outer squared minus r inner squared times, we have an expression for dA that we got up above, so that's 2 pi r dr. And so now I'm gonna just rearrange this. In the end, we're going to do an integral in terms of that variable r. So let's keep all the constant stuff by itself because we can pull that outside of the integral. Keep all the stuff involving r on the other side. So we have 2 p pi. Ooh, the pi's cancel. Yes. It's turning around. 2p over, no, r outer squared minus r inner squared. And then times r dr. Okay. Now we're trying to figure out, what we're trying to find is the moment that's applied by that friction. This normal force isn't a friction force. So now we have to figure out what the total friction force is on that ring. This seems like a little bit funny, like a little bit of a funny thing to do. Because if this thing's rotating, what's the direction of the friction force here? Well, it's rotating this way. At this spot on this infinitesimal ring, the friction force is that way, right? At this point, it's that way. You know, it's in different directions the whole way. But the key thing is that when we try to figure out the moment that's applied by that friction force, each one of those is perpendicular to each one of those forces is perpendicular to the moment arm. And so we can just, we can treat it all as a single moment. That's why we've divided it up into rings like this. Okay. So the total friction force, total infinitesimal friction force on the infinitesimal ring force of friction. Well, actually, this is an infinitesimal ring, so it's an infinitesimal force. The force of friction is just equal to the coefficient of friction times the normal. Infinitesimal normal. And so we can write that as it's what we had for dn just times mu, so 2p mu over r outer squared minus r inner squared times r dr. And now the fourth step is the total moment produced by that friction force. So the total infinitesimal moment applied by EFF. Well, every point on that infinitesimal ring is a distance, has a moment arm of r from the center. And so dm is just equal to r, the force of friction. So now just substitute in what we got before. We have all the constant stuff, 2 times p times mu over r outer squared minus r inner squared times r squared dr. And now finally we have the infinitesimal moment produced by that infinitesimal ring, and now we just integrate over the whole body. So total so the total moment, m, is just the integral from r inner to r outer of dm. So that's the integral. Let me pull the constant stuff outside. So that's 2p mu over r outer squared minus r inner squared times the integral from r inner to r outer of r squared dr. And so that's equal to, if you take this integral, you get r to the third over 3. So I'll pull out the 3 also. So we get 2p mu over 3 times the quantity r outer squared minus r inner squared. And then times r cubed, evaluated from big R inner to R outer. And so the final form is 2p mu times the quantity r outer to the third minus r inner to the third over 3 times the quantity r outer squared minus r inner squared. So the kind of problems that I'll give you will have numbers in them, but I want you to be able to go through those 5 steps. You would think that maybe it sort of looks like there'd be a way to cancel those two things, r outer to the third minus r inner to the third divided by the one with the squares, but there isn't. So that's as simple as it gets. Any questions about that right now? Notice that it does get simple if it's a solid circle, the cross section, and not a cube, because then those the r inner cubed and the r inner squared are gone, and then you just have a r outer on top. Then you can cancel stuff. Okay, so let me go through an example with numbers. So let's say we have a solid cylinder, and there's a force pushing these two together of 10,000 newtons. And let's say that the radius is 0.1 meters. So if this cylinder is at rest, what's the maximum external moment that could be applied before the cylinder starts to rotate? So step one, we're going to calculate the force per area. And that's equal to 10,000 divided by pi r squared. Since the pi's cancel, I'm just going to leave the pi in here. It'll go away later, so we might as well not introduce that round off error. So this is 10,000 divided by 0.01, well, pi times 0.01. And so that is 1 times 10 to the 6. So 1.0 times 10 to the 6 divided by pi. And next, for our infinitesimal ring, we want to calculate the infinitesimal normal force. We're talking about this ring with a thickness of dr and a distance from the center of r. So dn is equal to 1 times 10 to the 6 over pi times the area of this ring. and that's 1 times 10 to the 6 over pi times, remember how to calculate the area of that ring? 2 pi r times dr. This is the one where we break it open and make a long rectangle. Excuse me. So 2 pi r dr. That's where the pi cancels. And so d normal is equal to 1.0 times 10 to the 6. There's a 2 there, so I'll nope. 2.0 times 10 to the 6 times r dr. And now the friction force, this infinitesimal friction force, is just equal to the coefficient. Oh, I didn't give that. I meant to. Pretend I did. Okay, so let's say that the static coefficient of friction is 0.1. Okay, so the infinitesimal friction force is mu dn. So that's 0.1 times 2.0 times 10 to the 6 r dr, which is 2.0 times 10 to the 5th r dr. Then the fourth step is to calculate the moment produced by that friction. So dm is equal to r dff. And so that's 2.0 times 10 to the 5th times r squared dr. And now finally, the total moment is just the integral of these infinitesimal moments. So that's equal to, if you pull the constant out, 2.0 times 10 to the 5th times the integral of r squared dr. And then what are the bounds of r that we're integrating over? 0 to r, right, 0 to 0.1, the radius of the whole structure. And so that is, so 6.6 repeating times 10 to the 4th, because that's this divided by 3. Times r cubed, evaluated from 0 to 0.1. 0.1 to the 3rd power is, so 1 times 10 to the minus 3rd. So the total moment is 66.6 repeating Newton meters. Yeah. So if you apply a bigger external couple than this to that cylinder, it'll start to rotate. Any questions about that? Okay. Let's do this. No, you know what? Let's stop. We can do more later. We can do more on Thursday. Okay. What do you think about that? Go like have ice cream or whatever outside? I think that's what we should do. Okay. So Thursday, bring questions if you have them. Otherwise, I'll do some examples with this. And I'll do sort of an outline overview of the class kind of thing. Okay.